My name is Chesney. I'm an assistant professor of biomedical engineering at Pennsylvania State University. This is the building that I get to do all of my work in, my research, and teach my classes. I'm super excited to tell you about it. Come join me. Now, being a professor means I do a lot of different things. Most of what people think of is teaching classes to undergraduate students, maybe graduate students. And I do a lot of that. In particular, I teach classes on what's called mechanics, which talks about how strong things are, how stiff they are. Both it could be, a piece of wood, but we really focus on, in biomedical engineering, on parts of the human body. So that could be your bone, for example. It could also be heart, your muscles, your tendons, different things like that. And so I teach students, again, how these different tissues are constructed, what they're made of, how that structure leads to the mechanical properties the tissue has. Again, how strong they are when they break, how stiff they are. And then we try to understand how that changes from different tissues. Also, when the tissue is maybe under disease or damaged, what changes there. And that can be really useful for understanding different diseases and what to do to prevent the disease of different parts of our body. The other class that I teach is something called mechanobiology, and that's kind of a complicated word, but you can break it into its two parts. So you have the mechano part, that's kind of, again, related to mechanics, and biology. And as you'd imagine, it's the interaction between those two that's the focus of that field and that class. And specifically what I mean is, what we also like to study here is what types of mechanical things can happen to cells. So for example, how much can a cell get stretched inside the body? What type of forces does it experience, or how hard do things push on it? And how does that change the behavior of the cells? Right, so that these types of forces, whether they're being stretched or not stretched, can influence how cells live or die, if they decide to live or die, how they grow, what types of genes they turn on and off, and what types of proteins do they make to change the structure of the tissue that they're living in. And so as my students and I discuss the different research that's going on right now in order to understand how mechanical forces and stretching changes cell properties and then changes the structure of the tissue, and that leads nicely into the other class that I teach, which is about mechanics and how the change in tissue structure then changes the performance of the tissue. And that's also very related to the research that I do. And so I think a lot of people don't recognize that college professors not only teach classes, but we do a lot of research, particularly at universities like the Pennsylvania State University. That's most of the time that I spend. And that our focus of our work is looking at tendons in particular. Again, tendons are parts of your body. You can see it really nicely in my forearm here. They connect our muscles to our bones and allow us to move our body. But there's problems that people have with tendons. They can break, and they can cause pain, and they can degenerate. And so in our lab, we study, the mechanical properties of the tissue, what forces are required to break the tissue, how stiff the tendons are, both in a normal situation, but also in disease states or repair states, as the tissue is trying to heal itself, for example. And then we again study how the mechanical properties of the tissue changes the behavior of the cells in the tissue. And can we learn how to improve the cells in how they repair a broken tendon, or prevent the disease from continuing to progress. So that's our work. I'll show you some cool experiments later on today, but that's pretty much everything that the focus of my work is in the lab. So one of the greatest things about being a college professor is basically I can do whatever I want and follow my own interests. So in some ways, I get to study whatever I want to study, and I get to teach whatever I want to teach. And so one of the things that I like the most is that I'm constantly learning new things, and I'm always being exposed to difficult and interesting problems, whether that be in my research, which I talked about, which was about tendons, or even in the class, as there's new research being done by other people, and I start learning about that so that I can most effectively teach that to my students. So I would say if you're interested in being a college professor, obviously you have to try hard in school, continue learning as much as you can. But then also, get excited about continuing to do that for basically the rest of your career and for your job. And in my particular path, one of the things that really kind of inspired me to continue on in this work was the recognition that I just like to discover new things, and I constantly like to learn. And the way that I got to where I am is essentially I went to college. I actually went to college for mechanical engineering, where I studied more traditional type of engineering topics like cars and trucks and building buildings and things like that. I then got a master's degree where I worked at Ford Motor Company. I built part of the steering components of the Ford F-150 pickup trucks. I even went to Michigan and put the things that I designed into a pickup truck. We drove it around a test track and we saw how it worked. And it was a really exciting project, but I realized that while it was challenging and really interesting, working on cars was not something that really excited me. And then I ended up moving to Germany for a year. I started doing what was called Biomedical Engineering, where I used my mechanical engineering techniques to design different types of motors and things to help design medical implants. I got really excited about that, and I worked for 2 years as an orthopedic design research designer, and where we built spinal implants and surgical instruments, and I worked with surgeons to make new medical devices that were actually used to help patients. And after about 2 years of that, what I recognized was that while that was, again, both challenging and very interesting, there wasn't a whole lot of risk and there wasn't that much learning. Once I got good at what I did it a lot. And that was interesting. It was great to take ideas and give it into surgeons' hands and see it getting used on patients. But I really missed the challenge of overcoming failure. And that's why I ended up coming back to what's called academia, becoming a professor, because here is the environment where everything that we do is brand new. Nobody knows how to do it. And that's, to me, the really exciting thing. And that's the great thing about being a professor at a university, is I get to choose whatever I get to work on, whatever I find interesting. As long as I can convince people to give me money through grant proposals that I write, that come from, let's say, the federal government or from different companies, I can work on any cool project that I want. And so in order to do that, I got what's called a PhD. I became a graduate student. I started doing research and learning how to do research really well. I then did something called a postdoctoral fellowship, where I started coming up with my own ideas to do research. And then once I had good ideas of my own, I applied to become a professor here at Penn State. And I've been working here for about 4 years. And I have a great group of graduate students who you'll meet in a second. And we're doing some really cool, exciting work. So I can't wait to show you. All right, this is my lab. This is where all the cool stuff happens. So let me show you the inside. Come on in. So in here, we have all of the equipment that we need to be able to do kind of the biological experiments that we do and some of the dissections. So some of this stuff is really just doing like heating up things. So this is a water bath. This is a heat block where we get the right temperature for some of our experiments. Over here we have a very sensitive balance, or a scale, to be able to measure the weight of all the things that we use, whether it's making solutions or our samples. Over here you can see this is basic like freezer and refrigerators to keep things cold, both like the tissues that we dissect out, but again also the chemicals that we use. Come around here, so what's nice is you can see we work in a very open lab, so we're able to see a lot of people while we're working and learn a lot of things. Over here we have some more fancy equipment. So this is called a centrifuge. This spins things really fast to be able to separate out the different either proteins that we're interested in or take away some of the chemicals that we don't want after we chop up our tissue and try to pull out some of the things that the cells are doing. Over here you can see that this is the machine that actually we use. Both of these machines we use to break up our tendons and our ligaments, again to be able to pull out the information that the cells are doing inside the tissue, again whether they're helping to repair things or if they're causing disease. And you'll see in a second we have our own 3D printing device to be able to make different types of cool components and sometimes have a little fun with it as well. And let me come over into another room where we have some of our microscopes and some of our cool equipment where we keep the tissue alive. One from here. So over here we have our dissection microscope and a dissection space where we take the tendons out of, let's say in this case it would be chicken limbs, but also we could do it for mice or rabbits actually. Here we have a basic microscope. It's called a light microscope, and we can look at cells underneath the microscope, and we can look at different sections of the tendons and ligaments on glass slides. This is a fancier microscope called the Confocal Microscope. It has a whole bunch of lasers over here. It is connected to a computer where you can see the images from the microscope right here in the computer. And what's super cool is we can rotate it around, and here what you're seeing is the surface of the tendon that's labeled in green. And so we can get the really fine details of the tendon structure that's important for understanding the mechanics. Here is called a biosafety cabinet, where we can keep cells happy and sterile, and us safe from whatever we're doing with the cells. So this is more of like a biological tool. And then on the other side, there's more dissection equipment. And also things that we call their bioreactors. So I'll show you over here. These are spaces again where this is called the Fume Hood that controls the flow of air only away from us. So it's if we're using anything dangerous, we all put the dangerous chemicals in here to make sure that we don't get sick from them. This is the opposite. This is called a clean bench where all the air blows out at us. So if we have things in here that we want to make sure that bacteria don't get into or it gets infected, the air pushes all the bacteria out, so we keep that stuff safe. And then these are called incubators. I'll show you this one down here. This one is empty right now, but this is where we put the cells that we take out of our tissue and we keep them alive. And we also put our bioreactors in here that pulls on our tendons so we can keep them alive while we're pulling on them. And just wanted to show you one of our bioreactors looks like this, where we have a load cell that measures the force that's being applied to the tendons. These move back and forth and they pull on the tendon, as you'll see later. And then we can hang different weights or motors to be able to control how much we pull. So that's our lab.
So, hi everyone, my name is Ben. I'm currently a fourth year graduate student here at Penn State University. My research focuses on tendon development. So, tendons are connective tissue that help transmit force from muscle to bone, allowing you to move your skeleton and move. So I'm really interested in how tendons are actually developed in embryonic stages of development. So in a pregnancy, babies that kick, they squirm, they move around, and with all that activity, it puts loads and strains onto the tissue. So I'm really interested in how that mechanical stimulation helps drive the overall maturation and development of the tendon tissue. Oh, what inspired me? Yeah, still trying to figure that out sometimes. No, so I was really interested in the human body as a whole. I always thought it was like really interesting in trying to figure out kind of what made us tick, why we were able to do the things that we were able to do. I did a lot of sports growing up, so I was always interested in what made one person different from another that allowed people to do certain physical feats and activities. And that was something that I wanted to explore more in a lot of my research. And as far as advice for other people that are interested in getting into this field, I'd say just like ask questions, be curious. I think that there's a lot of things out there that are cool and interesting, and if you want to learn more about something, just ask somebody, and if someone doesn't know, just keep looking for answers. I feel like that's the best way to really get into this field of research and what I'm doing, but also just really great life habits to have. So here we have our dissection desk, where we can take our tissue and physically dissect it to isolate out different tissue and body parts of interest. So if you want to come in real quick. All right, so here we have an embryonic chicken leg, where you can see its muscle up here, and you can see all of its individual toes down here. So what I want to do is I want to isolate out individual tendons that control and flex and bring up these little toes. So to do that, I'm going to use my little scissors. This is where it's really awkward. So now I'm just cutting some tissue. And now I'm going to slowly peel this back. If I can't get it. And now I'll have access to all the individual small little tendons right in here. So what I'm going to do now real quickly is just make a small cut right here at the muscle, which releases the tendons. And now if I'm very, very careful, I can now tease these out of the joint, and now we'll have small little individual tendons. And now I can keep going and now make another small incision up here. Now I can just pull out the individual small tendons. All right, and there it is. And now if I have a small dime for scale, you can get an idea for just how tiny this little tendon is. And now I can take that and then I can do a number of different experiments to test some of its properties to understand how these tendons actually develop. All right, so one of the ways that we can also look at this tissue is with something called histology, where I can take that limb and actually slice it super, super thin. So here you can see what that limb's cross-section looks like when it's put on this slide. And then once it's on that slide, we stain it, where we are able to color different parts of the tissue depending on what it's made out of. And once we do that, we can then look at it under a microscope, like you can see here. And here you can see what that section actually looks like under the microscope. So this stain targets something called collagen, which is one of the main components that or puts together things like skin, muscle, tendon, and bone. And here you can see a cross-section of our hind limb, and right here you can see all of our individual tendons that together help control and flex all your digits. All right, so another thing that I'm really interested in is understanding its mechanical properties, or how much force or load can go across the tissue. And one of the ways that we look at this is using this unique setup. So this apparatus right here is able to tug and pull on our tissue. And with that, we're able to understand how it bears load and how it breaks and fails. And we also do this on top of something called a confocal microscope, which in comparison to the light microscope that you guys just saw, is able to give us much more detailed information at a much smaller scale and understanding what's happening here. So one of the cool things about this microscope is that it's able to get depth. So we're able to get the entire underside of the tissue and get a much more accurate representation and understanding of how this tissue's structure and function is changing. All right, so once again, I study a lot of chicken development. So to study that, I need to be able to allow our chickens to develop in-house in our own lab. So to do that, we have these incubators that allow us to take our chicken eggs and then develop them out to specific time points for our studies. So here you can see the individual chicken eggs sitting on a rotator, and this incubator keeps it at the correct temperature and humidity level so that it can grow naturally.
Hello guys, my name is Krishna Pedapalu. I'm a fourth-year PhD student in Penn State Biomedical Engineering department. My research is on tendons, specifically how they get injured. It is very common injury. We have seen it in Kobe Bryant, David Beckham, actors like George Clooney, even Dwayne "The Rock" Johnson. So it is very common. Even my lab mate and my roommate has it. So my work is to understand how tendons get injured. How I do it is I take out tendons from mouse and rats, load them externally, and see how the cells inside those tendons behave. Are they happy and healthy? Are they degenerating and diseased? And understanding those cues will help us make better rehabilitation program. Maybe it will help us diagnose the problems earlier than the injuries, and overall it will just make people healthier. The reason I got into biomedical engineering is kind of indirect. I was really interested in like how things are built, how things work. So my bachelor's was actually in mechanical engineering, but in my bachelor's I realized that human body is like a machine itself. So I decided to go into understanding how human bodies work, and that's how I got into biomedical engineering. I would say do what you love, and believe it or not, all the math that seems very irrelevant and unnecessary now is actually super useful when you get into research. This is where I do my mice Achilles dissection. In humans, if you look at this picture over here, here is the calf muscle and here is the ankle, and your Achilles tendon connects your calf muscle to your ankles. And similarly in mice, we have the calf muscle here, the ankle here, and this is the Achilles tendon. So I will remove this now. and then mount it over the grips. Bioreactor. And we load it by moving the grips.
Hi, my name is Lauren Pascal. I am a second, soon-to-be third-year PhD student here in the Chesney lab. I came from the University of Florida in a chemical engineering background. What first got me into science was I wanted to follow in my grandfather's path. He was an engineer. And then I just kind of always had a passion for biology ever since I was a young age. Both my grandparents passed away to cancer before I was 16, and it really made me question how biology works, what's going on in the cells, like why did this happen, how can we better prevent it. And ever since then I got involved in research ever since I started in university. My biggest piece of advice to do it is just find your passion and pursue it, whatever that may be. So if you are interested in science, start joining science clubs or math clubs or whatever you find interesting, and just pursue your dreams that way. I currently work on ACLs. As you will see some of my work later in the video, I want to see why ACLs are one of the most common orthopedic surgeries in this country. And so what goes wrong is they'll tear during sports like soccer, football. And when you have a surgery, there's only two types of graft options. So you can either have like a cadaverous donated tendon, which are called allografts, or a tendon that's taken from yourself, from a different part of your body, and implanted in your knee, called autografts. Now, for young active individuals, such as ourselves, we are 3 times more likely to re-rupture our grafts if they are donated. So there is some kind of deficit mechanically in them, and I'm trying to figure out why and what's going on. In addition to wanting to know how strong our tendons are, we also want to know what genes are turned on or off in our tendons. So we put our tendons in these vials to where we then have it with these beads and put it in this machine that will break it up. When we turn it on, the beads are going to be moving really fast to help break up into tissue to bring what's inside the cells outside. So after we are done breaking up the tendon to get the cells broken up, we'll put it in these ball plates to be able to read the gene expression. So I'll take this, which is as a pipette, and I'll put them in the wells to where we then put them in a fancy machine so we can get a number of what genes are turned on or turned off. So we'll get an idea if the tendon is healing itself and the good genes are turned on, or the tendon is destroying itself and the bad genes are turned on.
So my greatest inspirations to become a professor and do research, at least when I was your age, was just being excited about learning new things. When I was a kid, I always, one of the things that I used to do, for example, is I would take apart I would take apart vacuum cleaners. I would take apart parts of my parents' TV, see if I could put it back together again, just see how it worked on the inside. I was always curious, and I was always driven to kind of find out more. And so my biggest advice is just continue doing that. If you're the type of person who's really curious about the world and wants to know how things work, and really isn't just satisfied with the easy answer that you might find on the internet, and wants to see it for themselves, whether that's, again, vacuum cleaners, or it's how animals work, or our human body works, or the sun and the astronomy, anything really. Don't let the world tell you potentially that that's silly or foolish or not worth doing. Continue to pursue it, pursue those passions that you have, and those things will give you the motivation to really struggle through maybe parts of classes that are not as interesting or difficult, because you can make the connections to really what interests you. And sometimes I think, particularly in school where you're taught just to learn the right answer and then just put that down on the test, and that sometimes the wrong answer is not valuable. I often think that the wrong answer is the most valuable thing, is because that's how you learn. It's not shameful to not know the right answer on their first try. And sometimes your wrong answer may come from a place that's a good thought in an interesting direction. And just because you didn't get the answer right doesn't mean that you weren't thinking about it appropriately. You're just thinking about it from a different perspective. And that different perspective can both be valuable, and it's just exciting to learn new things. So continue putting yourself out there. Don't be stressed out about being right. Focus more about what can you learn, and put yourself in challenging situations where you may not know the right answer, because that's how you're going to learn the most. If you always put yourself in situations where you already know what the answer is, it's not going to be as interesting, right? And you're not going to learn anything. And I think that's the biggest thing about if you wanted to become a researcher and you want to become a scientist, you need to be comfortable with being wrong. I'm wrong every day of my life. Even though I know a lot of stuff about mechanics and biology, I'm wrong every day. And I like that. That's what excites me. And so don't lose that curiosity. Gain the confidence of being wrong. Doesn't mean that you're not intelligent. It just means that you're curious and you're learning something new.
Hello everyone. Today we're going to learn about the movement in our hands and what our tendons in our hands do to correspond with the videos that we had seen from the research at Penn State. So did you ever hold a cup? You know, you're grasping onto a cup, or you're holding a pencil to write. It has to work together with the tendons in your fingers to move your fingers so you can grab something, or you know, hold something for a long time. They combine with muscles if it's really heavy. So today we're going to do a little DIY activity, and we're going to make a hand to try to show you how to the tendons work in our hand. So we'll try to do that. We'll run through step by step. So as we get started, the first thing we want to do is we are going to need a piece of paper, and we are going to draw or trace our hand. And then for the sake of time, I have a couple things that are already pre-made. So we're going to cut this hand out. So I've made my hand already, and I'm going to cut it out. So I end up with just my outline of my hand. So when I do this, the next thing we're going to need is you're going to need some straws. Drinking straws are fine if you have some straws at home. And you're going to need a pair of scissors. So if you're a youngster out there and you need a little help from a parent or an older brother or sister, make sure you ask for some help when you're cutting. And we're going to cut pieces of the straw to simulate some of the joints or the bones in our hand, you know, as we look at that. So each finger has 3 small bones in our hands. So if I would look at one small bone here, one small bone here, and you can feel those in your hand, and then I would look at another small bone here. So what I'm going to do to get those to stay is I'm going to use a little bit of glue, and I'm using super glue just because I had it on hand. You don't need very much of it. If you have Elmer's glue, some kind of school glue, that will work as well. And we'll put one at the tip, one at the middle part of our hand, and one towards the bottom of our finger. So each finger should have 3 of those, and our thumb will have 2. And you can feel those in your fingers. All right, when you move your finger, you can feel them. So, and then in our hand, we have some longer bones. So to simulate the longer bones, we're going to cut a longer piece of the straw, and we will connect it down here. And when we do that, We will do that for all 4 fingers. Make sure you clean up the glue if you can. So your hand should look like, when you have all 4 fingers and your thumb done, it will look somewhat similar to this. And then what we're going to do is, I've grabbed some string. This looks like I borrowed it off my kids. It's a bracelet making string, and we're going to feed it through each straw. Sometimes you can use a toothpick to help you out. And then when you get it out the other end through the straws, what I had done for my final one is I folded it over the end, and I just put a little piece of tape right here to hold it at the end so it didn't come back out. All right, so you'll do that for every one. And when you do that, you end up with a finished product that sort of looks like this. So the yellow string going through simulates the tendons, and the straws simulate the bone, and obviously we have our hand. So if I would pull on one, it would move, that tendon would move my pinky finger, then my ring finger, then my middle finger, index finger, and even my thumb. So if I was going to make a fist, I would pull on all of them, and I would be able to make a fist if I was going to grab something. And if I wanted to write, you know, I would have my index finger and my thumb. You know, it would simulate, hey, maybe I'm grabbing a pencil. All right, and you can start to see how your hand moves. So that's the tendons that help with movement. Now obviously our muscles in our hand, and if you build up your muscles with some grip strength, that can help you in different things. If you're, you know, playing sports, or you're working in construction, or you're a painter, you know, obviously this movement and strength is very important. So hopefully that gives you a little bit of a simulation of the tendons in our hand and how they work, and hopefully you can make this at home. Like I said, it doesn't have to be perfect. You know, it just gives you an idea of how different things move. So, you know, a lot of times, you know, as I can get in here, somebody giving the peace sign, and you got 2 fingers up there giving the peace sign, you know, or you're number 1, you know, number 1, maybe my team is number 1, you know, on that end. So our tendons are really moving us to do anything like that. So hopefully this helped you out today, and you enjoy making this DIY activity at home. And I had a great time making it with you today. Thank you.